Good morning. It is my pleasure to introduce today's colloquium speaker, David Weinberg. David was the project scientist of SDSS and two of the main threads of his research are galaxy formation and large-scale structure. If I told you about all of the threads, I think he would not get any time to speak today because his interests go beyond cosmology, beyond astronomy, even into the realm of art. It's really broad interests. He is the chair of the astronomy department at Ohio State University. And today he is going to be talking to us about decoding chemical evolution and nucleosynthesis. Thanks.
Thanks. Well, it's great, fun to be here, and I won't play this whole thing again, but we'll show you the first part again. So I was drawn into this field mainly by the Sloan APOGEE survey, and this is just this is a time-lapse movie of one night of observations at the Sloan telescope. And so at the beginning of the night, our observer, in this case Karen Kimuchi, comes out, removes one spectroscopic cartridge from the back of the telescope, puts on another one, and takes it back to the bay, and there she's done, and then the doghouse rolls off the telescope, it gets set up for the night, and that on a sufficiently clear night, that process happens 8 times. It happens once when it's light, and the rest of the times when it's dark. And so, if you watch this movie, you see a telescope go somewhere, point there for an hour or so to get observations, and then Karen comes out again and does that same whole process again, and there are calibration observations and so forth. And the Sloan survey has been operating for about 20 years now. And we're probably open half the nights. So basically, if you do this 3,500 times, you get a lot of data covering a wide variety of things, and that allows you to do a lot of different science, ranging from cosmology to planets to decoding the chemical history of the Milky Way. So, beginning with observational motivation, this is a, not quite sure what happened to Felsing here, but this is the kind of Ur diagram of chemical evolution, distribution of stars in the space of metallicity, here measured by the iron abundance relative to hydrogen, and a ratio of alpha element abundances, in this particular case magnesium, to iron. And always this bracket notation is, it's a ratio relative to the solar ratio and in log. So plus 0.3 means that the magnesium to iron ratio is 0.3 dex higher, a factor of 2 higher than it is in the sun, and solar abundances would be here. So we've long known that the more metal poor stars tend to have elevated alpha abundances relative to the sun, and we think that's because they were enriched entirely by core collapse supernovae. Core collapse supernovae are very good at producing alpha elements, where you add an alpha particle to a carbon nucleus. So that gets you things like oxygen, magnesium, calcium. And then type 1a supernovae add iron and iron peak elements, but not much in the way of the alpha elements. So as you go more metal rich, the ratio of alpha to iron goes down because the denominator here is growing faster than the numerator. So I'll have more to say about that later, but that's the basic picture. And already, certainly by the early 2000s, it was evident that if you look at stars in the thick disk, stars that go far above the plane, relative to stars that stay close to the plane, filled in open circles here, that they are chemically different, and that at a given metallicity, the stars far from the plane tend to show more of this alpha enhancement. It's a more recent version of this from Adebekian et al. So that's so a fair amount of what I'll be talking about is related to that diagram in some way or another. So apogee is something that began in SDSS 3. In SDSS 3, we got high-resolution infrared spectra of about 150,000 red giants, and that's continuing in SDSS 4 now. And by the end of SDSS 4, we expect to be up to about 400,000 stars, and getting into both hemispheres. So SDSS 3 was just observing from Apache Point, so we couldn't see this part of the galaxy. But SDSS 4 is also observing with a new apogee spectrograph from Chile, from Las Campanas Observatory, so that allows us to fill in this part of the galaxy. If we look at just apogee 1 from SDSS 3, here's the sun, and this is basically the distribution of apogee stars. So you can see some of them get to the far side of the bulge, mostly cover this quadrant of the disk, and then in apogee 2, we'll get better coverage of this part of the disk and the bulge. And then our ambition in SDSS 5 is to, instead of just having this set of pencil beams, to actually get continuous coverage of the galactic plane and go up another order of magnitude in stars with high resolution spectra. So in terms of this kind of diagram, the first thing that you can do is you just get more stars. So this is looking at stars near the sun and going from 800 to a few thousand. So you can start to see additional details of structure. But the really important new thing with apogee is partly getting to a wider variety of elements that I'll come back to towards the end of the talk, but also because we're observing red giants, we can see them over much of the galaxy. We've got large numbers, and also because it's infrared, you can look in those gunky parts of the galaxy where all the stars are, and so we can actually compare these kind of distributions in the solar neighborhood to what happens high above the disk, or in the bulge, or in the inner parts of the disk, or outer parts of the disk. And you can see that these distributions change as you look in different parts of the galaxy. So this is, so far my all-time favorite plot from apogee, from a paper led by Michael Hayden in 2015. It's showing that same distribution of stars in the alpha element to iron versus iron to hydrogen, but now as a function of position in the galaxy. So we go from the inner galaxy, 3 to 5 kiloparsecs, solar annulus here, going out to 13 to 15 kiloparsecs, and then also looking at height above the plane. So these are stars within half a kiloparsec of the midplane, 0.5 to 1 kiloparsecs, 1 to 2 kiloparsecs above the plane. And there are all sorts of things you can see in this diagram. So basically what we were seeing before was the sum of these three, the solar annulus. So in most places, there is some high alpha sequence that's up here, but the lines are just drawn here, but they're the same in all the panels. And you can see that where there are stars with elevated abundance ratios, they're pretty much following the same locus wherever you look. But the relative number of stars that are on this upper locus and lower locus depends a lot on position in the galaxy. The inner galaxy, they're kind of all lying on this track. The outer galaxy, none of them are. And as you look in the midplane, you go to from high metallicities down to steadily lower metallicities as you move out. That's what we expect from the galactic abundance gradient. Something that was more of a surprise is just doing taking these stars and counting them as a function of metallicity, so making the metallicity distribution function. And in the solar neighborhood, it's long been known that that's roughly Gaussian if you look in log of metallicity, so that's the green, maybe it's the cyan here. And I think, mostly people thought, well, Gaussians are the kind of usual thing that you see. And there are some kinds of models that will give you a Gaussian-ish distribution. But really, once you see it in the whole context, what you see in the inner galaxy is that this distribution looks very different. It's sharply high metallicities with a tail to low metallicities. And then in the outer galaxy here, it's the opposite. The red has its long tail to high metallicities. So really, there's a steady change in the shape of the metallicity distribution as we go from the inner galaxy to the outer galaxy. And the sun, the solar anomalous just kind of happens to be in the middle of that where it's symmetric. So we'll come back to that point. So that's observational motivation. So now I want to go to theoretical models. And so this part I'll mostly focus on what shapes things in those alpha, the evolution in that alpha to iron space. I'll mostly be talking about this paper, a little bit from the first and third. So these are my students and postdocs, and I have two Johnsons that I collaborate with on this on these projects. So Jennifer Johnson, who's a faculty member at Ohio State, and James Johnson, who's a second-year student. So for Brett Andrews' PhD thesis, we were sort of looking towards this APOGEE multi-element abundance data set and trying to think about what were we going to do with 100,000 stars with 15 different chemical elements measured for each. We were thinking in terms of measures of dimensionality and principal component analysis. But before we had the data, we thought we'd better start out by constructing some theoretical models for what we would expect. So part of Brett's of this paper, Brett, is looking at predictions for a wide range of abundance. But we actually found that we ended up spending quite a lot of time just in trying to understand different aspects of models in this alpha to iron versus iron to hydrogen space. And here we chose oxygen as our representative alpha element. And looking at the many different kinds of parameters that people change in these chemical evolution models, and what we found was that if you're looking at the evolutionary tracks in this space, that the two parameters that matter the most are the outflow mass loading. So stars form, some fraction of the some amount of gas gets ejected, and if you change the ratio of ejected mass to star formation, then you get very different endpoints of these tracks, although the early evolution looks similar. And the other thing that makes a big difference is the star formation efficiency. So if you're converting gas into stars relatively quickly, then you get a knee in this diagram that is at a fairly high metallicity. If you're forming stars inefficiently, then this knee occurs at lower metallicity. So, and there were lots of other things that you could change that some of them made some difference, but overall these were the most important factors. And then another thing which we hadn't really anticipated before Brett started doing these models, although I do think it's familiar to people who have been doing this stuff for a long time, is that the abundances evolve, but then they kind of stall. So there are points here going up to 4 gigayears, and then between 4 gigayears and 12 gigayears, almost nothing happens. And so I would say prior to actually seeing these calculations, I sort of thought the way evolution in these diagrams worked was things were along, then they went down, and then they continued to march up in metallicity, but at solar alpha abundances. But that's not actually what happens. Really, a population evolves, in these models at least, to some equilibrium abundance, and then it just kind of sits there and keeps forming stars at that abundance. So this long analytic paper started out with trying to understand, see if we could understand analytically where those equilibrium abundances came from. And then turned out we were able to go further in actually coming up with, I think, pretty useful analytic models for describing the whole evolution of stars in these diagrams. So the assumptions going into these models are they're single zone models. So there is a reservoir of gas that forms stars, and metals get distributed from the stars into that gas reservoir. This here is showing that there is inflow and there is outflow. So this is not a closed box set of models, but the one zone means that it is fully mixed, but there is always gas, there is allowed to be gas accreting, and there is allowed to be vapor coming out. So the oxygen, I'm going to focus on oxygen and iron, and oxygen is assumed to come just from core collapse supernovae, and the iron coming from both core collapse supernovae and type 1a supernovae. And for the analytic models, one of the things that makes them work is assuming that the supernova yields are independent of metallicity once you average over the whole initial mass function, and that's a good approximation compared to typical predictions for these elements. So there are other elements where that wouldn't hold, but for oxygen and iron, it's a reasonable assumption. And then the core collapse supernovae go off essentially immediately, but the type 1a supernovae go off over some amount of time, and the particular functional form that we assumed is that there's an exponential distribution, so you get the type 1a rate has some minimum delay time, and then it's constant for a while, and then it falls off exponentially. So again, the main adjustable timescales are, the main adjustable parameters are eta, this ratio of the outflow to the star formation rate, and the star formation efficiency timescale, which is the gas supply divided by the star formation rate. So here's the differential equation for the oxygen mass in this gas reservoir. So there is input coming from star formation. So this is the yield, and I've detailed all the subscripts here. So it's the mass of oxygen produced by core collapse supernovae per unit mass of stars formed. So for a standard IMF and the assumption that all stars above 8 solar masses explode, this number is about 0.015. So if we form 100 solar masses of stars, you get about 1.5 solar masses of oxygen back. So that's the source, and then there are two sync terms. So this is, ZO is the oxygen mass fraction of the ISM. And as you put oxygen into the newly forming stars, you're using up oxygen, you're taking mass out of the ISM at this rate, but you're also throwing oxygen out in the outflows, so there's also this sync term. And then this represents gas that's coming back because a lot of the mass, particularly the lower mass stars, goes into the stars and then it comes back out when they become white dwarfs. So R is the recycling fraction, which for a standard IMF is about 0.4 or 0.5. So that's the same differential equation. I've just collected terms over here on the sinks. This is the equivalent equation for iron, and it looks almost the same, except now there's an additional source coming from the type 1a supernovae. And here it's not the instantaneous star formation rate that you care about, it's the star formation rate averaged over the delay time distribution of the type 1a supernovae. And so you can almost see from this that there will things will approach some equilibrium. So for a constant star formation, there's going to be some value of CO at which this term and this term will cancel out. And that equilibrium oxygen abundance is just the yield divided by 1 plus eta minus R. And then for a constant star formation rate, just the same thing applies for the iron, and the equilibrium abundance of the iron is the same thing, except you add the two yields. So the equilibrium abundance depends on the yields, and it depends on the outflow rate. And then the ratio of oxygen to iron just depends on the yields because the 1 plus eta minus R cancels out. This is my last slide of equations, but just showing you how this goes into time evolution. So if you ask about the oxygen, then you start off at an abundance of 0, you end up at this equilibrium abundance, and the time scale for getting there is the gas depletion time scale. And the gas depletion time scale isn't just the rate at which you're putting gas into stars. Also, you have to account for the fact that you're losing gas to the outskirts, you're losing some back from recycling. But that's the time scale at which you are processing gas through the stellar population, and so unsurprisingly, that becomes the time scale on which you can approach this equilibrium. And then if you have not a constant star formation rate, but an exponentially declining star formation rate, then this equilibrium abundance changes by some amount, and the time scale generally gets longer, although it only gets much longer once you have a pretty rapid decay of the abundances. So the other, so this is what happens for any element that's getting instantaneously enriched. A lot of the work in the paper is going into also doing these analytic solutions for the type 1a supernovae, and so there the delay time adds some additional complication, but it turns out for many circumstances you can still solve those equations. So then here's what those things look like. Again, the point that you already saw in that first diagram from Brett Andrews' paper is that these tracks depend mainly on tau star, the star formation efficiency, and eta. So I'll show some examples to illustrate that. This is just one model with an exponential star formation history and points every half gigayear. And now if I compare to something with a lower outflow rate, then the evolution is overall similar, except that this equilibrium abundance is higher because I'm not losing oxygen as rapidly, and so I follow the same sort of track, but it goes up to a higher abundance. And I should say, in these diagrams, the solid is showing the oxygen, the open circles are showing the iron, and so it's the fact that the iron is taking longer to climb up here, that gap between them is what's giving you an elevated ratio here, and then when they converge, you're down at solar abundances. This panel is showing the star formation rate, and this panel is showing that metallicity distribution function, the things I was showing you from APOGEE. Let's see, so this is going to a high outflow rate, so now there's a big sink of oxygen, it's being lost from the ISM rapidly, and so things settle at some lower oxygen abundance, but basically the same ratio of oxygen to iron. And this is going to a low star formation efficiency. So still the same star formation history, but the implied gas supply is different because gas is going into, a given amount of gas is going into stars more on a longer time scale. And so in this case, the gas doesn't get to as high an abundance before the type 1a start to become important and drive it down. So that's basically those dependencies on the outflow and the star formation efficiency that we found in the numerical models come out pretty naturally in these analytic models. Then you can also look at the dependence on the star formation history. So here's a more rapidly declining star formation history, so a pretty short exponential time scale. And in this case, what happens is, so the equilibrium abundance gets higher because of this term over here, and that's a consequence of the fact that you're dumping in elements into a steadily declining gas supply, so that boosts the metallicity, and also that you end up with a lower, or sorry, higher ratio of iron to alpha elements, and that's because the iron is coming from type 1a supernovae that formed a while ago when the star formation rate was higher. So you're changing the ratio of these two things. So that changes the endpoints. This is the opposite case. If you go to a constant star formation rate, then the track is fairly similar to the exponential decline, except you don't get to as low an oxygen to iron. And probably the biggest analytic feat of my career, and I'm not a very analytic person, so it wasn't, it's not that big an analytic feat, but was to actually get all this stuff to work for a star formation history that first rises and then falls. So it's linear times exponential. And I think for many purposes, this is actually a better model to use for star formation histories. What's interesting in that case is that you end up at the same equilibrium abundances, but you have fewer stars at low metallicity, and you have you have a much slower approach to equilibrium. So you still have the same eventual equilibrium behavior, but it takes longer to get there. And the analytics, you can also take mix and match things. You can do superpositions of an exponential and a constant, or a linear exponential and a constant, and so forth. So you can do a fair amount of playing around with these models. So you saw those metallicity distribution functions. I'll just make one general point, which is that, so if we focus here on the iron distribution, that if you have a system that is accreting gas at a rate that is comparable to the star formation rate, so it's not running out of gas, then you generically get these metallicity distribution functions that are quite strongly peaked at high metallicity, and that's because they get to equilibrium and then they just keep forming more stars at that abundance. On the other hand, if you have a gas-starved system, in the limit of no inflow or inflow that is slow compared to the star formation rate, then the star formation rate is declining, and that's where you get these kinds of turning over metallicity distribution functions. And that's because the metallicity is continuing to go up, but the approach to equilibrium is slow, and you're forming fewer stars by the time you get to higher metallicity. Now, a closed box model, which is often used because there are analytic formulas you can write down, is basically this green curve. And so that is a good approximation for a gas-starved system, but it is actually generically very different from what you get for an accreting system. The other interesting thing we found with these solutions is in order for an analytic solution, you have to have the parameters like the outflow rate and the star formation efficiency stay constant, but you can put in a sharp change and then sort of take together two different solutions at the boundary between them. And so that's some approximation to a more general smooth change of parameters. But there are quite interesting things that can happen. So these are 4 different examples of funny behavior and color-coded in text here. So the green is something where after 2 billion years, the outflow parameter just rapidly drops from an 8 of 8 to an 8 of 2.5. So first it's evolving here. It would like to end up at an equilibrium abundance around this. But then the outflows get less efficient, and the system thinks, oh, actually my equilibrium abundance should be over here, near solar. And so it changes and marches up towards a solar abundance and then settles to equilibrium. Let's see, the red curve is, I would say, the most interesting. So that's an opposite case where you start out with an outflow mass loading of 1.5. So they're outflows, but they're not super efficient. And then at later times, the efficiency of outflows goes way up. And so then what happens, the system evolves to this equilibrium, then the equilibrium changes, and the stellar population actually evolves backwards from high metallicity to low metallicity. So I think, once you think about sources and sinks, it becomes obvious that this can happen. But I would say prior to actually doing this, I always thought of chemical enrichment as a monotonic tracer, and the question was how linear it was, but it can in fact run backwards. Then the other 2 curves are what happens if you suddenly change the star formation efficiency. So the cyan is a starburst by suddenly increasing the star formation history. Now you're dumping in a lot of core collapse elements rapidly compared to type 1a. And so you get this upward hop in the oxygen iron, and then it settles back down here. And the black curve is the opposite. Stars are forming, and then star formation suddenly becomes much less efficient. And in that case, you're still getting the type 1a iron from those stars you formed a while ago, but not so much core collapse, so you get this downward excursion, and then eventually the system wants to head back up to a new equilibrium, but it hasn't reached that yet. So these kinds of changes, which might be induced by mergers, might be induced by changes in accretion history, might be induced by outflows, becoming more or less efficient as you change the gravitational potential. All these sorts of things can actually produce various kinds of interesting behavior. And so some of these we've been, James Johnson and I have been investigating with pretty simple numerical models. So we're just integrating the same differential equations, but now allowing bursts of star formation. And one thing you realize is that there are different ways to make a burst, and they have at least somewhat different effects. So this is a case where you suddenly dump in a bunch of gas at 2 billion years or 6 billion years. So now in this diagram, you go to here, and then the metallicity goes down, because you've dumped in a lot of gas, which here is assumed to be primordial. And then you get that same hop that you saw in the previous case, up the higher alpha to iron, and then it tracks back down. You can do that more gently by just changing the infall rate. But if you instead keep the gas supply constant but start consuming it more efficiently, you still get these hops. You don't first get this backward jump, so you get a different morphology here. So partly we're interested in these models for looking at dwarf galaxies where the star formation histories are thought to be more bursty. But also one of the things that I'm interested in observationally is how much scatter is there in these ratios in different parts of the galaxy, and what causes that scatter. So in a smooth model, there isn't really a source for scatter in those abundance ratios, but these kinds of, whether they're bursts or slow oscillations in the star formation rate, are generally going to produce scatter in alpha to iron ratios, and that can be some diagnostic of the star formation history. Okay, part two. This is, I would say I have long had an ambition to write a paper with this title, where long means like 3 years, and I haven't. So I would just tell you some of my thoughts on it, and particularly about the kind of surprising role that deuterium has as a potential constraint on answers to this question. But if you'd like an exercise to be thinking about during this part of the talk, as you have no doubt taught your undergraduates, all of the oxygen atoms or carbon atoms or whatever in your body were once inside a star. But the hydrogen atoms could have been inside a star or could have come straight from the Big Bang. So the exercise for you to think about is what fraction of the hydrogen atoms in your body were once inside a star. And the key thing that you, well, actually I'll come back to that. So the general arguments about galactic winds, one is galaxy masses are small compared to the baryonic masses of their halos, and therefore explaining galaxy masses either requires you to prevent gas falling into the galaxies, or in most of the models that I and many people in this room work on, we have a lot of gas driven back out. And if you want to get the Milky Way mass in a Milky Way mass halo, then the eta you require is something like 2 to 3. Observationally, we see evidence for starbursts in very rapidly star-forming galaxies today. We see it in generic star-forming galaxies at high redshift. But there's not much evidence for winds at the present day in galaxies like the Milky Way, M101, etc. And so that could be because they don't have them, or it could be because they're hard to see. So we have the question, winds we know must have been important for getting the galaxy masses right, but were they just a remnant of the past, or are they still around today? And the chemical evolution argument says, well, you still need to have pretty high outflows today, because otherwise the oxygen abundance will want to get up to 2 or 3 times solar. And so matching solar abundances in our models really requires eta of 2 to 3, and it's very hard to get away with eta of 0. So potential loopholes in that argument. One is that the oxygen yield is actually lower than we're assuming, and I just recently found out that one of the main chemical evolution groups with Francesca Mateucci and others, their oxygen yields are actually 3 times lower than the ones that we use, and that's principally because they assume a much steeper IMF. and therefore they don't have the high mass stars that are making the oxygen. So really, these you are often told how people, we use this table and this table and this table and this combination, but you're very rarely told in a paper what the oxygen yield actually is or what the iron yield actually is. And so it can be, it took me a long time to realize that partly we were getting different answers because we had very different yields, and I don't know which one is right, but I know it makes a difference. Another possibility is that for the chemical evolution is that the galaxies are ejecting metals, but they're not actually ejecting gas at the same rate, so metal and mass wins. It could just be that the equilibrium abundance is high, but the oxygen abundance hasn't reached equilibrium. Overall, I think that solution is hard just because it doesn't actually take very long to get to equilibrium. So, if you turned off winds 100 million years ago, sure, but if you turned them off, 3 gigayears ago, then you should get to supersolar abundances pretty quickly. And then there are other things that you might play with redistributing metals within the galaxy without actually ejecting them. So those are all possibilities. So where does deuterium come in? So the observed deuterium abundance in the interstellar medium varies from sightline to sightline, but it's thought that that variation is because of depletion on the dust grains. And if you take the kind of upper envelope of those distributions, then the observed abundance of deuterium is about 90% of the primordial deuterium value. And the thing about deuterium is that it is destroyed by stars. So if deuterium atom falls into a star, then it doesn't come back out as a deuterium nucleus. And so this is the equation for oxygen. The equation for deuterium, there's a source from infall at the primordial deuterium abundance. And then there's a sink that you lose deuterium either by putting it into stars or by ejecting it, and you don't get any back out, so there's no R piece out here. And then if you have an exponential star formation history and a constant star formation efficiency, then you can show there's this relation between the infall rate and star formation. And so if you have higher outflows, then there must also be higher infall to sustain the star formation rate. Therefore, more of your interstellar medium is primordial, and your deuterium to hydrogen ratio will be closer to the primordial value. So that's the basic idea. And then it turns out that there's a bunch of different models on this plot. Maybe there's just 3 on this plot, but there are other ones also in the paper. And all of them end up following this curve described by the circles pretty well, which is this little formula here, that the deuterium abundance in the ISM is the primordial abundance, divided by 1 plus the recycling fraction times the oxygen metallicity of the ISM divided by yield. I was led to this equation because in the equilibrium it becomes exact, but it turns out to hold pretty well throughout evolution. And if you take what I told you was a standard oxygen yield, 1.5 solar masses of oxygen for every 100 solar masses of star formation, and you assume a standard recycling fraction of about 0.4, then you end up at solar metallicity, you end up with a deuterium fraction that's 87% of the primordial value. That's in very good agreement with the observations. And I think the uncertainty on the observations is something like this, and what's very hard to decide is whether that is a 1 sigma uncertainty or a 2 sigma uncertainty or something else. And I would actually love to see someone go back to this problem with costs and get a better measurement of the deuterium abundance of the ISM, but I'm not competent to do it myself and haven't persuaded anyone else to do it yet. This is just showing, this is from a paper by Frika van der Voort looking at the fire simulations, and there are, the gray band is this deuterium to primordial deuterium ratio measured in the or inferred from the simulations, and then the curves here are the fit of that model, so of that equation. And so even when you have a complicated star formation history and mixing and outflows and all that, this accounting still basically works. So So when I first got this result, I thought, well, this is pretty boring because it just shows that any chemical evolution model that gets the oxygen abundance right is guaranteed to get the deuterium abundance right. So deuterium seems like this wonderful check on chemical evolution, but actually you're guaranteed to get it right. But in thinking about it a little more, I've come to almost the opposite view, namely that there are things that you can change in the chemical evolution model that actually will screw up this agreement. And those changes are things that are interesting to try to rule out. So one of them is a much lower oxygen yield because in this equation, if I change this number, I'm clearly going to change the predicted relation between deuterium and oxygen. And so in this particular figure, here again are the observations. Here is all supernovae exploding, so our standard oxygen yield. But if you just say all stars above some maximum mass collapse to make black holes instead of forming supernovae, then you don't get out that oxygen. The IMF average oxygen yield goes down, and you follow the black curve here for the predicted deuterium abundance. And so if the deuterium abundance is at least 80% of the primordial value, then that tells you that stars up to at least 35 solar masses must be exploding, because otherwise the yield would be too low in order to get agreement between deuterium and oxygen. Another thing you can also consider a metal enhanced wind, and with the metal enhanced wind, then what happens is you're ejecting metals, but you're not ejecting gas, so you don't get as much infall. And because you don't get infall, you're not getting this primordial helium enrichment. And so this shows our standard model has just an enhancement factor of 1. The metals are going out at the ISM metallicity. By the time you get up to enhancement factor of 2, then the predicted deuterium abundance has fallen to about 80% of the primordial value. And certainly if you go up to very high values like 3 or 4, then it's very hard to still get this agreement. So overall, I think the way deuterium figures in here is that 2 of the most obvious loopholes are at least disfavored, and I won't yet say ruled out because there are uncertainties in the deuterium abundances, and maybe there's other funny games you can play with the nature of winds and what they eject and so forth, but basically the 2 most obvious loopholes are disfavored. So I think this strengthens the chemical evolution case that the Milky Way and M101, etc., should still have galactic winds today, even though they may be hard to find. Okay, and the answer to this exercise, yeah?
When you say outflow, it could be that the metals started going to the hem of the Milky Way
right.
rather than outside.
That's right. So they don't need to leave the virial radius, and they don't even need to be prohibited from coming back. But what they do need to do is, if they come back, they need to come back with a lot more primordial material mixed in. So stuff can fountain, but it's got to fountain and be diluted. If it just fountains and comes back at the original metallicity, then from the point of view of these models, it's as if it never left. Thanks for the clarification. And yes, so the answer to the question is that basically, since 90% of the hydrogen in 90% of the deuterium in the ISM is primordial. 90% of the hydrogen is primordial, which we know because the deuterium to hydrogen is 90% of the primordial value. Therefore, most of the hydrogen atoms in your body actually never did go through a star. And roughly half of your, once you figure out how many water atoms you've got, basically about half of the atoms in your body were never inside a star and half of them. So half of your atoms come straight from the Big Bang. I'm actually going to skip this part so I can get to the last part, but this is a series of papers about trying to understand that distribution of alpha to iron ratios as a function of position in the galaxy. So trying to explain these diagrams. I will just make one particular point because I highlighted this change in shape, and we think that the most plausible explanation for this change in shape is radial migration, that stars can be born at one radius, but then can get moved by spiral arm or bar perturbations to a different radius over the history of the galaxy. And that this inner thing is actually what I've argued is the generic shape for a metallicity distribution function. But then in the outer galaxy, you can have stars that were born at higher metallicity in the inner galaxy that come out. So in the outer galaxy, on the red histogram, these are stars that were actually born at smaller radii. But this radial mixing process is kind of symmetric, but there's more stars inward to go out than outward to go in. So radial migration quite naturally takes this kind of birth metallicity distribution function and then makes it change as a function of radius. Okay, let me finish with talking about a paper which I had really aimed to have submitted before I came here, but I didn't, hence the sad face, but this is with these collaborators, and it's taking that plot, let's get that one, it's taking that plot from Hayden et al., but now trying to do it for a bunch of different chemical elements that APOGEE measures. And specifically, so if you've never seen this version of the periodic table made by Jennifer Johnson, you should look it up, it's great. Color-coded by where we think different elements come from. And so the elements that are examined in this paper are the ones in cyan are alpha elements that are thought to come largely from core collapse supernovae. The yellow ones are light elements, but they have odd atomic numbers, and if they have odd atomic numbers, then they're expected to have different nucleosynthesis that should depend on the metallicity of the star, and then iron peak elements where they have a significant type 1a contribution, and I've separately colored them by whether they have odd or even atomic numbers. So those are the things that we're going to look at. And the first thing we did was the kind of obvious generalization of the Hayden et al. Plot. We did X to Fe versus Fe on H in all of these different zones. This particular plot is for aluminum, and it looks kind of like a mess. So in particular, the black points are the median relation in all these different zones, and you don't really see this expected signature of metallicity-dependent yields of aluminum, and it looks quite different in different parts of the galaxy, so it looked rather complicated. So we did two things that ended up simplifying the picture a lot. And one of those things was to look separately at these high alpha and low alpha populations. So this is the distribution back in that magnesium to iron versus iron to hydrogen, and we just divide them and look separately at these stars, which will be colored red, and these stars, which will be colored blue. So now we go back to that same diagram. We've chosen somewhat larger bins, but it's still going out in radius up in distance. And you can see that if you look at the red stars and the blue stars separately, they actually have similar distribution, similar median sequences as a function of location, because the red and blue lines are the same everywhere. But what's changing is as you go from one location to another, you're changing whether you're looking primarily at this population or primarily at this population. And that's changing as a function of metallicity, so it changes this overall thing. So the second important change that we made was instead of making iron our reference, making magnesium our reference, because iron comes from two different sources, core collapse and type 1a, whereas magnesium is thought to come pretty much just from type 1a. And so once you do that, then these sequences become the same in all locations in the galaxy, and they're basically the same for the high alpha and low alpha population. And now at last you actually see this expected signature that as you go to higher metallicity, the ratio of aluminum to magnesium increases. And previously that was being masked by the fact that you kept changing the denominator as you looked in different places or as you looked in as a function of metallicity. This is the OMG plot, but it's actually not very interesting because what you find is the ratio of oxygen to magnesium is solar everywhere, and that's what you would expect because oxygen and magnesium should both be coming predominantly from core collapse supernovae, and indeed they basically are the same in the two populations and the same as a function of galactic location. This is manganese to magnesium versus magnesium to hydrogen, so say that 5 times fast. I tried to find a tongue twister emoji and I could not. But this one's more interesting, that now there's a big difference between the high alpha population and the low alpha population. And there's a strong metallicity dependence for these sequences, but it's still the case that, the red lines and blue lines are defined for the entire sample, and those stars, wherever you look in the galaxy, basically lie along the same sequence. So what we found from doing this is that basically this chemical cartography for all these different elements is sort of separable into two pieces. There's something that determines the alpha to iron ratios, and that depends on position in the galaxies. But once you know the alpha to iron, then everything else is basically predicted by the supernova yields. So you can take the entire sample and just make these trends for the entire sample. Here it is for alpha elements. For the light odd Z elements, for the iron peak elements, you see the odd ones have these strong metallicity slopes, the even ones have weaker metallicity dependence. And the separation of these things is a diagnostic for how much type 1a supernovae contribute to that element. So then the paper sort of concludes by developing this, call it two-process model, that just says for any given element, there's a contribution from core collapse and there's a contribution from type 1a. There's each of those processes has, so the core collapse process has some ratio of oxygen and calcium and so forth versus magnesium. The type 1a has some ratio of all those things relative to iron. Those things are allowed to have some dependence on metallicity, but it's assumed to be a power law to keep the number of parameters small. And then we can fit that to these observed median sequences. So here there's a model fit to the triangles, here for the alpha elements, here for the light odd Z elements. Here's probably the most interesting one to look at for the iron peak elements. And so what you see are things like on the left, there is this strong metallicity dependence for vanadium and manganese and cobalt. Manganese, this big separation means there's a big type 1a contribution to manganese, and cobalt, on the other hand, has much less separation. That indicates a much smaller contribution of type 1a supernovae to cobalt. Nickel, interestingly, comes in as an iron peak element, but only there's only about half as much of the nickel coming from type 1a as there is for iron. So it's a more alpha-ish element than you might have thought. So then there's lots of different directions you can go from this. So a consequence of this model is if you tell me the iron and magnesium abundance of a star, I will predict every one of its other elements, at least the ones that Apogee has measured. And that prediction works pretty well throughout the galactic disk. It doesn't work perfectly, and so it's interesting what the scatter is, it's interesting what the trends are, it's interesting to compare this to supernova theory predictions, and it will be interesting to go look at dwarf galaxies, look at the halo, look at the bulbs, look at Sagittarius, but I think we've got a model that pulls out the thing that we know is most important, that there are different ratios of type 1a to core collapse, and that pulls out the metallicity dependence of those units. So these are all directions we want to go, and I had some philosophical comments, but I will actually just leave up not really a conclusions, but the outline with a little visual trigger for each, so you can ask questions.
All right, questions for David?
Yeah.
So the Milky Way is not isolated; it sits in the local group, and in fact, the dark matter halo of the Andromeda galaxy is already overlapping with our. So, and it's very similar. The sister galaxy looks very much like ours. And so, how do you expect, have you thought about how the wind from Andromeda may feed into the Milky Way and vice versa?
So I think
maybe we see some signatures of that already.
Yeah. So there certainly can be mass transfer and metal transfer between galaxies. I think that, and we and some other people have looked at that in cosmological hydro simulations. My guess is that if we're talking about the Milky Way and Andromeda, it's a relatively small effect, just because by the time you get out there, you're pretty diluted. Probably the place where this is going to be most important would be maybe you could potentially have influence of the Milky Way on small satellites within the Milky Way. Overall, I think this is probably not a big process, but we can look at it to some degree. I will say one thing that I looked at just with the analytic models is usually I assume that what's falling in is primordial, but you can instead say you can let it have some other metallicity. And what matters is what's the metallicity of the infalling gas relative to this equilibrium metallicity of the model. And so if you have 0.1 solar metallicity gas falling in, then as you might guess, that's a 10% perturbation on something that's going to be, it's going to make things at solar metallicity.
Clusters at 0.3.
Yeah, so it could be a bigger effect.
Are apogee stars, the ages of apogee stars measured well enough to directly compare to the predictions you make for your models?
Yeah, so so part of what I skipped was a recent paper by Diane Foyet on looking at the age metallicity relation, but for a number of different elements as measured in apogee, and then I've constructed some models to compare to those. There are several different ways of getting ages of apogee stars. So in Diane's paper, she's taking ones that have well enough measured parallaxes that she can get them from the location on the HR diagram. The thing that's proved particularly useful is stars with astroseismology from Kepler, and now they'll be coming with TESS. So that allows you to get accurate masses, and if it's a red giant, so you know it's evolved, and the mass gives you the age. So age is very rapidly becoming an interesting additional parameter. I think the interesting things from Diane's study are that the solar metallicity stars in the solar neighborhood are on average the youngest stars. So the low metallicity stars are older. That doesn't really surprise people. But the high metallicity stars are also older than the solar metallicity stars. That, again, is plausibly explainable in these kind of radial migration models, because you form stars early in the middle and then you migrate them out, and that's the metal-rich population. The actual median age that she finds for solar metallicity stars is only about 2 gigayears. And that is very, if that's right, it's very hard to reproduce with any kind of smooth star formation history. So I think that's a case where I would say, either there's a problem with that observational result, or the Milky Way, at least at the solar annulus, really did have a big enhancement of star formation a couple of gigayears ago, which I would have said, was quite implausible, but when people look at the star formation history of Andromeda, that's just what they're finding there. There was this huge enhancement, a gigayear ago, and then it's fallen back off. So maybe there's a similar thing.
Maybe a satellite there.
Yeah.
M33.
That's right. So it could be a satellite perturbation did it in M31, and maybe Sagittarius or something else did it in the Milky Way.
I saw some questions in the back, yeah.
Yeah, how does your interpretation of the metallicity results change if you account for the recently claimed major merger from about redshift 3 that is being claimed by a lot of Gaia groups, and they say that the metallicity, the perturbing object that dropped in was pretty metal rich, right? So out to about 30 kiloparsecs, like the metallicity you're inferring from your models.
So you mean the Gaia sausage or whatever you decide to call it, right? So I think that so I'm very interested in looking at metallicities of things in the in the halo and substructures in the halo. So I think there's, but I would say I don't think the stars from that object, as I understand it, are a substantial fraction of the current stars in the disk. So in that sense, I think they're a small perturbation until you actually go out and look at the halo, and then when you look at the halo, then they may be a large fraction, at least in some zone, and that would be very interesting to look at. I think possibly it could be an object that caused a perturbation that changed the star formation history.
I saw one. We'll take these last two questions. So Erica, and then
So it sounds like it's pretty likely that the Milky Way has a wind, or it's plausible. Do you have thoughts on how you might go detect it?
So so there are forms in which it would be easy to detect, and unfortunately, those forms are ruled out because people look and they haven't seen it. So the challenge is if it's a kind of relatively cool wind coming off, then the kinds of things that people like to look at are sodium deabsorption, and there's stuff that's just is hard to measure. So we've pushed on people like Tim Heckman and Crystal Martin about what could you do about this, and they said, well, there are clearly versions, plausible versions of winds that are really hard to see. I still keep thinking that with IFU data sets, things like Manga or Khalifa, that there should be some kind of clever stacking thing that someone can do to actually pick off something that would look sort of like these. I think cosmic ray driven winds are very attractive for this scenario because they allow you to kind of gently lift stuff off the disk without blowing it out in some very rapid star formation region. So theoretically, I think those things are attractive for explaining this sort of chemical evolution, but it is not clear observationally how you detect it.
Well, there are the Fermi bubbles.
Right. So I do think that. So I should say, I think a loophole for this chemical evolution argument is that it says you have to be blowing stuff out of the galaxy, but it doesn't say where. And in particular, if you have gas flowing radially through the galaxy, it can be being enriched as it goes along and get to the middle and then be ejected from the middle. So I think the combination of you can't have it not blown out because then you would just accumulate too many metals in the middle. But if you blow it out from the middle and have it go through the disk as it goes along, I think that's a possible solution.
One last question.
So I have this comprehensive catalog of subworks from SDSS. I worked with Andrew West on this one, and we do see similar separation in metallicity between the different types of subworks that you show in your diagrams between the different populations.
That's interesting. So they're low metallicity, they're low iron abundant stars,
yes,
but they also have this bimodality.
Yes, and you can also separate them by different populations in the galaxy. So they also show this kind of separation as well as a dynamically heated population versus this population.
And do you have, or is it feasible to get other abundances for those stars besides alpha and iron?
So we actually have a full spectrum from SDSS for those stars.
But there's some segue type spectra, they're not apogee spectra.
No.
Okay.
All right, let's thank David again.
Yes. Yes. Well, good questions. All ones I've been worrying about. So.
Well, some of the questions I had you already answered.
Okay, good.
And it seems like you thought about most of the projects. All my comments were
Yeah, I think someone was asking last night about what it was like to
Yeah, I was looking.
start working in a field that really haven't worked in before. I would say there are some downsides, but there are upsides to it that I think
Of course, that's why I'm waiting.
you haven't absorbed all the conventional then. You kind of you end up not making
Interesting.
something.
So,
I remember when I came here,
I was on my phone and I wasn't sure.
and
Also, I was in discussion yesterday.
and this is a traditional field that a lot of people are working on. Now we have much better data and better understanding of the summation, so it's
Yeah.
a big expression.
so maybe we
And Charlie Quantum is
Let's see,
basically.
I sent it out to the CFA all, so
You
I'm
both
not
came
sure
from
what
the same
happened.
advisors, so it's not
Yeah.
surprising.
I came yesterday largely so I would be able to talk to Charlie.
Yeah.
I spent 3 hours talking to
I
Charlie.
mean, you
And then
share
I said,
similar
you know,
names in that
schedule
sense.
Yeah.
This afternoon, but.
Anyway, I'll see you in the
Follow up
afternoon.
with him
Good.
and see if there's time you could
Yeah.
talk otherwise. Yeah, please talk. David,
Yeah.
I am gonna set my stuff down. I'm gonna walk to the ladies' room.
Yep.
I'm coming back for you, so
Okay.
I'm not abandoning you.
Okay.
I need to take you in about less than 5 minutes upstairs, but I will be back.
Okay.
Hi, I'm Antonia.
Nice to meet you.
Hi. I was just wondering, I was on travel yesterday, I missed your discussion about the science to art
Yep.
thing, and I'm actually doing art on the side, like glass and mosaics. And I'm interested to do like a collaboration with a UK glass artist. I work a lot with MSSL. I don't know if you know that that's the space laboratory to
Okay.
University College London.
Okay.
And they do have like every year they invite an artist and they do these collaborations. And so I'm thinking to do something like that. I'm actually a solar physicist, but I do like other things as well. So here's the.
Well, that sounds fantastic. So what's the kind of work that, the kind of artwork?
That she does or that I do?
Or that you're aiming to do? So
so
you're planning to collaborate on a project?
Yeah, I would like to sort of represent solar eruptions with sort of glass, you know, in a glass setting. I have these MHD simulations of eruptions, and you know, I have them color coded, sort of semi-transparent, and I think if you make this in glass, it would look amazing. And so I was wondering if you have time at some point. I'm here tomorrow.
I'm not here tomorrow, so
if you would be able to meet with me at some point,
My schedule is
I have some
until
questions.
4:30. My flight's not till 8, so I think I could meet with you at 4:30.
Oh, 4:30 is fine.
What's your office number?
It's P139.
Okay.
Yeah. So
What's
so
your name again?
Antonia Savcheva, SAVCHEVA.
Okay.
Yeah, I'll
Good.
be in my office. So.
All right, so I'll see you there for about 4:30.
Yeah.
And I'll have to.
Yeah. Okay, great. Thank you.
Okay, so this is the part where I wander you through the building.
Yeah.
To the point that you're very disoriented and lost. We're gonna go up 2 floors, through an office, up another half flight of stairs.
Okay.
Yeah. Just warning you that.